Okay, this is my talk about Euler's theorem and the Königsberg bridge problem. And this is the beautiful city of Königsberg, as it appeared in the 18th century. It's a city set on two sides of a river, with two islands in the middle of that river. And so that's four land masses, and they are connected to each other by the seven beautiful bridges, which you can see here highlighted in green. You can't actually see the actual bridges, it's fine. And this guy here is Leonhard Euler, who was a mathematician in the 18th century, and he was interested in the question, is there a walk I can take through this city that crosses each of these beautiful bridges, and crosses each bridge only once? So a walk that crosses every bridge exactly once, and this question led to the start of graph theory and also modern topology, and we're going to talk a bit about it. So you can try and solve this problem if you like. I've tried to come up with a solution here. I found a walk, but I didn't manage to cross all the edges. I've sort of missed this one bridge here. So there's this question of, if I can find a walk, that's great, but what if I can't find a walk? Is it possible that there is no walk that crosses all of these bridges at once? And if so, how would you show that there was no such walk? And to answer this question, Euler drew this figure on the right, which we now call a graph, that basically represents all the structure of how the bridges on the land masses connect to each other in Königsberg. So a graph is made up of vertices, which are these circles, and edges, which are the lines connecting them. In this case, the vertices correspond to the different land masses, so the two sides of the river and the two islands, and the edges correspond to the seven bridges of Königsberg. We're interested in a path, which is a sequence of vertices connected by edges, and we're interested in a particular kind of path, which is now called an Euler path, which is to say a path that uses every edge exactly once. So, this question of, is there a walk that crosses every bridge exactly once, is just the same as saying, does this graph have an Euler path? And one more note about terminology, I'm going to have to talk about the degrees of vertices at certain times. The degree of a vertex is basically the number of edges that meet at it. So in this example here, the top vertex has degree 3, and you can see that the north bank of the city also has 3 bridges coming off of it. The middle island has degree 5, and so on. Okay, so to try and figure out if we can find this Euler path, we're going to think about what would happen if you're just sitting on one of these islands or one of these vertices, and you're watching someone else walk in an Euler path. So if that person was starting on this island, let's say this island which has degree 3, we'd see them start to this island, and then we'd see them leave by one of the bridges, and then a little bit later we'd see them come back on another one of the bridges, and then we'd see them leave again by the third bridge, and after that we wouldn't see them again because they've crossed all the bridges that they can cross that connect to this island. So that'd be the end of that story. If the walk wasn't starting on this island, then at some point we would see the person come across the bridge onto the island for the first time, then we'd see them leave again, and then a little while later we'd see them come back to the island via the third and final bridge, and after this point they would have to stay here because they've crossed all the bridges they can cross, so the walk has to end here. So they're either starting at this island or they're ending at this island, and that's basically because of the fact that this island has 3 bridges coming off. It's got an odd degree, and that's kind of what leads to this thing of either you are starting here or you're ending here. For vertices of even degree, you can kind of tell a similar story. So if you're starting on this island, then maybe you'll leave, and then you'll come back, and then you'll leave, and then you'll come back again, and then you'll have to stay where you are because you've used up all your bridges, so you're starting and ending in the same place. Or maybe you don't start on that island, and then we'll see you arrive on the island and leave again, and arrive again and leave again, and then we won't see you again, so you will, if you didn't start on this island, you didn't end on this island. But the important thing from these different cases is that if you've got a vertex that has odd degree, that vertex has to be either the start point or the end point of your Euler path. And that leads to Euler's theorem, which says that a connected graph has an Euler path if and only if at most 2 of its vertices have odd degree. So now we can apply this theorem to the city of Königsberg, and the sad result is that there is no nice walk that crosses every bridge exactly once. There's not an Euler path, and we can see that by looking at the degrees of the vertices. So there's one vertex that has degree 5, there are 3 other vertices that have degree 3, so that's 4 vertices, all of which have odd degree. That 4 is more than 2, and so there is no Euler path. Sad times. Okay. With my remaining time, I want to talk about the other direction of this theorem, because this theorem is kind of basically telling us two things. We've kind of argued that if there is an Euler path, you have to have at most two of these odd degree vertices. But the great thing about Euler's theorem is it also says that the converse holds, that if you have any graph that has at most two vertices of odd degree, then there must be an Euler path. So how do we do this? How would we go about proving this? So here is an example graph. It has two vertices of odd degree, those are the ones in blue, and all the others have even degree. And now what we do to construct an Euler path is we basically just look at each vertex in turn and just guess what we think the path is going to look like when it crosses our vertex. So we make a guess here that the of this vertex that the top and the right edges are going to be connected, and the left and the bottom edges are going to be connected. We sort of make a similar guess for each of the vertices in our graph. Obviously, if you have a odd degree vertex, then you're going to pair up some of the edges, but you're going to end up with one left over, and that's kind of going to correspond to your start or end point. And then once we've made this guess about all the vertices, we just join them all together along the edges, and ta-da! We now have a nice thing that covers all the edges. Hooray! But wait a second. This isn't a path. This isn't a properly connected path, because there's actually two connected bits to it. There's this one long path in dark purple on the left, but there is also this pink cycle on the right. And so this isn't the thing we wanted. This isn't a path that visits all the edges at once. So what are we going to do about it? Well, it's still okay. We can fix it, because we can look at one vertex, say this one, where the two different paths meet. And what we basically do here is we make a different guess about how the path should intersect this vertex. So rather than saying that the two left edges and the two right edges will be joined up, we say that, for example, the top two edges and the bottom two edges are going to be joined up. And now doing this change suddenly joins up these two paths. So now these two paths were previously disjointed become a single thing, and so now we have a path that visits every edge exactly once, has a start and an end, and it covers the whole graph. Great. So that's Euler's theorem. The connected graph has an Euler path, if and only if most two vertices have odd degree. One of my favorite theorems from graph theory, and I hope you understand a little bit about why it's true now. But the other thing I'd like to mention in the last slide is there's kind of a sister concept to Euler path called a Hamiltonian path. So an Euler path is one that visits every edge exactly once, but a Hamiltonian path is one that visits every vertex exactly once. And a fun open question you might like to try and answer is there a quick way to decide if some graph has a Hamiltonian path? And we know that the answer for Euler paths, it's this thing about seeing if there are at most two vertices of odd degree. But for Hamiltonian path, no one knows. No one knows if there is or isn't a nice way of figuring out whether a graph is Hamiltonian. And if you can find one, then I'd be very interested in talking to you, because that would mean that you have solved something which is equivalent to the big problem of P versus NP, which is a fundamental unsolved question in computer science. It would also mean that you qualify for the Millennium Prize, and you'd get to receive $1 million for finding a solution, and you'd make a lot of computer scientists very unhappy. And that's the end of my talk. Thank you for listening.